Hello everyone, it is Saturday again, and we are presenting on the Deep Learning book. This is the Deep Learning book review meetup group. So we want to give you some background information on our group and what we're doing here today. We are reviewing Chapter 9, Part 1 of Chapter 9 of the Deep Learning book outside of MIT. And so just to give you some background information on our group and why we're doing this, we decided that as a community we wanted to learn this material, and so we have participants come in and volunteer to read the information of a chapter ahead of time and then do a short presentation for us. They put together some slides or just some talking points, and then we get together on YouTube Live and just kind of talk about it, ask questions, kind of familiarize ourselves with the information. We decided that this is the best way for participants to gain the most experience in understanding out of the material, to have a volunteer present each week. So this presentation can be as short as 10 minutes, as long as an hour, depending on the depth of the material covered. We also decided to cut the chapters into smaller portions to make it more digestible. After a certain point in the book, it seemed to get very, very intense, and a lot of material was being covered. So fortunately, we decided to do that. And if you'd like to join us as a presenter, please click on the presenter sign-up form that's located both in the YouTube Live session as well as on our meetup group. And that meetup group is AI and Deep Learning Enthusiasts, and you can find that online on meetup.com. We have these online sessions. We also have in-person sessions that take place in San Francisco. We also host workshops and different events in the area. So let's go ahead and get started. Today we have a presenter, and I'm sorry I didn't ask how to properly pronounce your name beforehand. Is it Sharif?
Yes, Sharif.
Okay, perfect, wonderful. And he'll be presenting part 1 of Chapter 9, which is Convolutional Neural Networks. Do you want to give some information about yourself?
Yes, so hi Laura, hi everybody. My name is Sharif Jazdra. I'm a software engineer. I've been in the wireless industry for the past 10 years, but more recently I got into machine learning, and in the past year or few months into deep learning. So I'm really excited about this opportunity to present to you the convolutional network chapter.
Wonderful, thank you.
I'll switch to it now. Let's see.
And also, while he's getting ready, we just want to encourage people to join the discussion, ask questions on our chat room. So if you see the chat room listed next to the video, you can go ahead and join in there, and then we'll be keeping an eye on that and making sure anytime you have a question or you want to add to the conversation, please do there. And then also, if you have a question that the presenter doesn't necessarily know the answer to, we do really highly encourage participants to go ahead and add to the discussion. So if someone else knows the answer, please jump in. This is really a community learning experience. Okay, great. Go ahead and get started.
All right. Can you see the slides?
Yes.
Okay. So let me get started then. So here are the chapter section that we'll be going through today. We'll go through a brief intro, introducing the convolution operation itself, the mathematical form it takes. We'll talk about why it's an important operation, why it's used, and how it can achieve a characteristic known as equivariance of translation. Then we'll talk about pooling, which is another operation that happens on top of it, and that will help us achieve invariance of translation. We'll talk a little bit about the convolution and pooling as an infinitely strong prior. And then the final section we'll go into is going through some of the variant used of the convolutional function.
Ask questions, kind of familiarize ourselves with the information. We decided that this is the best way for participants to gain the most experience in understanding out of the material, to have a volunteer present each week. Sharif, it seems like you have the live video also going in the background.
Good. Okay, here we go.
Okay.
Yeah, sure. All right. So what is the convolutional network? It's a special kind of neural network, and it's adapted to a grid-like input. We can use it either for a 1D time series or a 2D image data. And at its core, it's using this mathematical operation called the convolution instead of plain matrix multiplication. in at least one layer of the network. So let's look at the operation itself. So the output of this function s is going to be equal to the integral of the input and what we call the kernel. So input is x, our kernel is w. We integrate over every value of the time t here. For every t value, we do this operation. The output of the operation is called the feature map. So this is a 1D example. So the book gives us this example of a noisy laser sensor that's used to estimate a spaceship position. So we get noisy measurements. When we are using convolution, what we can do is achieve a certain smoothing. So if we look at it closely, what it's doing is calculating a weighted average of the input. If we carefully use W and we multiply these various values of W with the values of X, we can achieve a certain smoothing. And in case of a laser sensor, the way to do it is to pick the values of W that backward in time degrade, such that we consider only the most recent measurements. And then the values in the future obviously have to be zeros. So we're weighting the past values. So this is a continuous version of the convolution. The discrete 1D version will replace the integral with a summation. And t here will be a discrete integer. So the 2D version will, for example, an image, will have a double summation. And then the I here will be the input. The K is the kernel. And
looks like we have a quick question, Sharif, already from the audience. So we have a question from Abdullah, who has asked, how can it be used in a time series analysis, clustering specifically? Do you know?
In clustering of time series, I'm not sure about a clustering application. If we look at the operation itself, I see it more as a smoothing operation rather than a clustering operation. But yeah, but I'm not sure about clustering itself.
Okay, perfect. Please continue.
Okay. So for the 2D cases, for the 2D case, one of the property of the convolution is that we can flip, we can sort of replace the input and the kernel, we can flip them. So we have the second version here. You can see the index I minus m and j minus n are on the input side rather than the kernel. And so in that sense, the output is the same for these two equations. So that's called the commutative property. And that's possible that commutative property is true because the kernel is said to be flipped. So the index of the kernel actually is decreasing when the index of the input is increasing. So that's when I'm talking about the m versus the I minus m. So in that case, the kernel is said to be flipped. But in practice, when we're using convolutional network, we don't use flipped kernel because they're not really adding anything to the kernel. So we use what's called the cross correlation. And you can see down there, instead of a minus, we use a plus. So it's I plus m or j plus n. And then we use the second version of the convolution, as we are summing over all the indexes of the kernel itself.
Okay, we have another quick question. So Varun has asked, what is a kernel? Could you please elaborate?
A kernel, going back to the simplest formulation of the problem, is this weighted function w. We're going to give it a name. It's called the kernel at this point. It has a set of parameters, and the goal of the training aspect of convolutional is to learn those parameters. So I will show a little bit later. It'll be clearer what that kernel is doing. So I will defer the rest of the answer to that time.
Yep, and we also had input from another participant that said it could be thought of as a mask or a filter. Do you agree with that?
Yes, you also called a filter, and think of it as a smoothing function is also a good way. You can think of it as a function that we're going to learn that will allow us to kind of achieve these three different attributes that I'm going to talk about in the next section. So let's wait a little bit, and then we'll maybe clarify that.
Thank you.
Let me go through an example, actually. This is an example from figure 9.1. And we have an input image, say not necessarily image, but an input matrix, a 3x4. The kernel is this other smaller size matrix, a 2x2 matrix with parameters w, x, y, z. And then so the operation of the input, the operation of convolution will give us the output here. So I have a little animation that will show how this works out in practice, I mean in the mathematical form. So in the top right here we have the formula. We have the input 3x4 matrix on the left, and the kernel a 2x2. The first so the output is S with I of j. So we're going to fill the feature map S at every pair of values of I and j. And at every pair of values I and j, we are doing this double summation over m and n. So m and n are the indexes of the kernel. So we're going to use, for let's say I is 1 and j is 1, so the first row, first column in the feature map. So this will take us to the first row and first column of the input, let's say A here. And we're going to use that kernel window and overlay it over the input at that location. And we're going to multiply every element at that location with the kernel, so element by element. So we're going to do A by W, B by X, E by Y, and F by Z. And so that's the inner product of the summation. And then we do the double summation, so we're going to sum all these products. And so in the bottom feature map, I show the sum of these products, A by W plus B by X plus E by Y plus F by Z. So so that's the output at location 1, 1. So next would be calculating at location 1, 2. So we slide the kernel. So in this case, we're moving it just 1 pixel, 1 element to the right. And then we do the same thing. We calculate the product and then we sum them. So we do this over all the indexes of the feature map. Are there any questions?
Nope, it looks pretty straightforward.
Okay, good. All right, next section goes into some of the attributes of convolution. So what does it allow us to do? So it's the three main characteristics is that it's achieving sparse interactions between input and output. It allows us to do parameter sharing, and then it can create equivariant representation. So let's go through each one. First is the sparse interaction. This basically says that our output units are not connected to all the input units. So looking at the right here, we have a fully connected dense network. We pick X3 as one input, and then we show how it's connected to all the outputs. But in the case of the convolution, we have sparse connections. One input, such as X3 here, will only be connected to a subset of the output, so S2, S3, S4. And that will be defined really by the size of the kernel. So in this case, we have a 1D, obviously there's a 1D case, and we have a kernel size of 3. So the conclusion here is that we have fewer parameters to learn, and so fewer computation. So in the dense case, the fully connected network, our amount of operation will be a function of m by n, where if you have m inputs and n outputs. And in the convolutional case, it'll be O of k by n, where k is the size of the filter again. So I'll use interchangeably filter and kernel at this point. Okay, and so O of k by n, and here we can choose k to be very much much smaller than m, and so we'll save a lot on computation. Another view of this is the concept of receptive field, and this is basically telling us that the nodes in the deeper levels will be connected to a bigger number of inputs. So at least indirectly. So for example, in this first layer, H2, the first hidden layer, H2, H3, H4, H2 is connected to only 3 input nodes, X1, X2, and X3. But G3, which is in a deeper layer, will be connected to H2, H3, H4, and then again X1 to X5. So it's connected to actually the full list of input. So the receptive field of G3 is all these gray nodes, and these are all the nodes that G3 is connected to directly or indirectly. So the second aspect is that we're sharing our parameters. We're doing what's called tied weights, and so the same parameters are going to be used at multiple time steps. So we showed earlier how we are moving the kernel itself in order to do the convolution operation. And so that's what I'm showing here in this 1D case. For a kernel of size 3, we're going to be moving the kind of sliding it from left to right, so it has only these 3 parameters, and they're going to be reused. That's what's meant by sharing. And then the picture shows this middle black line, which is supposed to correspond to the middle parameter of the kernel. And so it's saying that in the upper picture, which is the convolution picture, we are reusing the middle parameter at every input location. And if we contrast that to the fully connected layer at the bottom, we only use the middle parameter once. So each parameter is really used only once, while in the convolution case, we are using the parameters multiple times, the same parameter multiple times.
And what would be the benefit of that?
Well, as I mentioned earlier, we have fewer operations.
Mm-hmm.
Fewer operations, so overall it's faster to compute. And but the most important one, I would say, the most important aspect of convolution is that it will allow us to capture the that third attribute, which I'll go through, which is equivariance to translation. So that basically tells us, so the convolution itself as a transformation, as a mathematical operation, is equivariant to translation. So moving an object in a picture, or let's say moving an event in a 1D timeline, a little bit later in time, will change the output by the same proportion, but just later in that time. So another way to say it, so if the input changes, the output changes in the same way. Or the book says also, if you do a convolution, and then you shift the pixels, you shift the image 1 pixel to the right, you'll get the same result that if you were shifting first and then convolving. So what this allows us to do is really learn or get in the output the same kind of effect for objects that are found that have been translated. So translation means moving an object, moving something in the picture to the right, vertically or horizontally, diagonally. It doesn't mean rotation or changing the scale of that object. So it just means moving it. And so convolution is basically allowing us to capture the fact that some aspect of a some object in a picture can be found in multiple locations. And with a convolution, we can find that pattern more easily. So that's what equivariance to translation. That's what is captured by this notion.
Wonderful.
But this does not allow us to capture rotations of objects or scaling, making object bigger or smaller. So because convolution is not equivariant to those transformations. Okay. Okay, next section, we'll talk about pooling, the pooling operation. So in this book, so typically there are two terminology used when we're talking about convolutional layer. One is, which is the left one is used in this book, is that convolution actually is really three phases. The first one is the convolution transformation itself, followed by this detector stage where you apply a nonlinearity like the ReLU. And then the third one is the pooling stage, which we'll define in the next slide. And some other people may refer to the convolutional layer as the first layer. That's the right column here. But in this book, the convolutional layer will encapsulate all three stages. So what is pooling? So conceptually, the pooling operation consists of replacing a certain area of the input with the summary statistics of that area. So in the picture here, I've divided 4x4 matrix into 4 regions, and I'm applying this max pool operation. A max pool is gonna replace each section with the maximum value found in one of the pixels here. So in the top left section, the max value is 6. So we have a 6 on the right, and then we have 8, 14, 16. So the max pool will reduce our input of 4x4 to a 2x2 matrix, with every value in the index being the maximum in the input section. There are other kinds of transformation. You can do an average of the section, you can do a layer 2 norm, or a weighted average. Those are discussed in the book.
Do you know what is the benefit of each one?
The benefit of each one?
Like why would you use max pooling over average pooling or over doing the L2 norm?
Yeah, well, at least one of the benefit of max pool is that it really allows us to get to invariance, but to small translations. So if we have a little change in the input, or like a kind of a translation to the left or to the bottom, it might not affect our output that much. And so that can be very useful for learning different patterns using different filters, but whose patterns are really rotations or scaling. And actually the next picture here, maybe not this picture, but okay, I have there's an example that is given of letters, and how we can use pooling to create invariance with regards to a rotation of a letter, or yeah, a rotation of a letter in that particular example. So that's kind of one benefit. And but with regards to the difference between all these three, it's not mentioned in the book, but they're all I think they are all things that one can try as hyperparameters and see how they perform. One can be, it might be that max pull is too strong an operation and it removes too much by just taking the maximum, and that an average of the value might perform better on a task. So it really depends on the task, I would say, and your empirical testing.
Wonderful, thank you. And there was another question by Varun. He asked, in what way is this taking the maximum value? And then we got an answer from Adil who said, in the example, the maximum value in each quadrant is picked. So maybe if we can elaborate on that a little bit more. So the top left quadrant, right, we have numbers 1, 2, 5, and 6. So in this case, the maximum value would be the 6. So that's what's transferred over on the right-hand side in that top left quadrant. So
Yes.
just for anyone that's watching, if that makes sense. And then like the same thing would be, so the top right quadrant, we have 3, 4, 7, and 8. So the maximum value would be the 8. And so that's the number that's transferred over.
Correct.
Yeah. Thank you. Please continue.
Okay. Well, this is another example that will illustrate the invariance property. So in the top one here, we have the example of these 4 input nodes, and we apply a pooling, a max pool operation. So it's a three size kernel. So the maximum of these 3 here will be propagated to the top. So as we move to the right here, 1 is the max value in these 3 sections here. So the top value is 1. And as you move to the right here, the top value changes to 0.2. And so if we had shifted all the inputs by 1 node to the right, like in the lower example, we've changed all the values of the input by shifting them. Nevertheless, the output actually doesn't change so much. I mean, 2 nodes have the same input. I mean, they have the same value still. So we've so half of the output remain the same, even though all the input has changed. All the values of the input have changed. So we have invariance. We have some invariance to translation. And here is the other example with the letters. So in this case, we are using multiple kernels over the same image. So earlier we talked about just one kernel, but this is an example with multiple kernel. And we're assuming here that the kernels have each learned a different view of the letter 5. So so a different orientation. So that's what we've learned in these. That's what they encapsulate. So as we get this new input 5, it bends a little bit to the left. Then the output of the left kernel will be highest compared to the other 2. And if the input number bends a little bit to the right, and then the rightmost kernel will give the largest value. So if we had a pooling operation on top of these 3 kernels, it will give us this max value in both cases. So at the top, we have that same value, even though at the bottom, we have 2 inputs that differ by their orientation. So we have sort of the concept, if you like, of 5 that's more constant after we've applied the pooling operation.
So what if the 5 was totally upside down?
So we would need a kernel that's totally upside down in order to capture that invariance. But so that really depends on the number of kernels and the training process for us to achieve that particular invariance.
So the model would have to be trained on on that type of image as well, is what you're saying.
You'd have that type of image, and you would have more kernels, so more filters. So here we only have 3. These 3 are just specific to this orientation. We would need to learn the upside down orientation as well.
Cool. Thank you.
Another thing that pooling can help us achieve is processing images of varying sizes. So typically, the output of the whole network is to do some sort of classification, and the top layers may be this fully connected layer, which expects constant input. With pooling, here we show 2 examples. One where we have an image of fixed size only. I mean, we can only deal with images of fixed size. And in the right column, we can deal with images of varying size. And so in red, I show the pooling operation. So the difference between these 2 is that in the left one, we're just doing pooling with stride 4. Means that we're just moving the pooling window, if you'd like, for 4 columns and rows at a time. And so depending on the input, we will get a different size or a different shape for the output. But in the right side here, it says the output of pooling is a 3x3 grid. So that means that whatever the input is, what this operation will do is fit this input to a 3x3 grid. And so the max pooling or the average, that will have to be done on a different size of the input based on that input shape. But the output will always be 3x3 by 64 channels in this case.
So we have another quick question from Abdullah. How do we determine the number of kernels?
So the number of kernels is a design choice. And that will be part of your whole architectural, all the choices that you have to do when you're designing your network and choosing your parameters. In this chapter, we don't go through, I mean, it doesn't go through those choices. I think there is one chapter in the future where we go into all those considerations. So I won't go into, I think we'll deal with that in a future chapter. I think it's, let's see if I have it here. Yeah, Practical Methodology, chapter 11.
Chapter 11? Okay, great. Thank you.
Okay. So section 9.4, it talks about this interpretation of convolution and pooling together as putting an infinitely strong prior on the parameters of this function we're trying to learn. So we talked about priors, I believe, in chapter 5. And so there are 2 types of priors, 2 types. The weak prior basically puts a prior distribution on parameters where that distribution has high entropy. So it's kind of spread like a Gaussian with a high variance. It could be like flat a little bit if you like. And so when you start with that distribution, when you're making updates to your parameters, you have more flexibility to change them to a value that's much more different than your starting point. But when you're using a strong prior, you start with this low entropy distribution. So it gives a lot of weight to just particular values. For example, like a Gaussian with low variance will be peaked around the mean. So that allows one to place almost 0 probability on some parameters, some values of those parameters, so making them forbidding. So what the authors are saying here is that we can interpret convolutional networks as if they were a fully connected network, with the addition of having an infinite strong prior over its weights. So So in the picture here on the right side, I have a fully connected network, and on the left side, I have a convolutional network. So there are these two properties of the infinite strong prior. First one is that we want weights for a hidden units to be the same as weights of neighbors, but shifted. So on the left side, we see this with the AB parameters that are repeated. So it's kind of the same as saying that the fully connected network should have this property, like two edges should have the same should have parameters that repeat when you shift to the right. And then the other is that weights must be zero except in the spatially contiguous receptive field. And so that's our sparse connectivity attribute. So all the weights coming in the fully connected case, all the weights coming from like into S1 from the inputs that come after X2, all these like the connection from X3 to S1, X4 to S1, X5 to S1, those parameters should have zero, should have a distribution, should be basically outside the density of the distribution. So they have zero probability, basically. So that's how we kind of turn off these edges. So it's one way to see convolutional network. So it's more interpretation. You can think of a convolutional network as a fully connected network, but with these infinite strong prior over the parameters of the weights of the edges. There are two considerations that they make in the book. The first is that there's a problem of underfitting when we use convolution and pooling if the prior assumptions really doesn't reflect the reality we're trying to capture. For example, if we are working on a task which relies on preserving precise spatial information, so you want to preserve the actual values of the information at every location. So convolution and pooling won't be useful. Another one is if local input area needs information from some distant location. So like our like output S1 in the previous picture here, S1 needs information that's in X5. If that's the reality of our task, then we're going to lose that information if you use convolution. So we might be underfitting. And one solution, at least from the pooling perspective, is that you could decide to do pooling on some channels, like some kernels, but not all kernels. So you could maybe underfit on just those channels, or maybe you could spread it out so that the channels where you don't have pooling will learn the patterns that get lost when you use pooling. So that's the first consideration. And the second one that they make is that it's better to compare convolutional network only to convolutional network in order to evaluate their statistical power. And the reason they give is that you could permute pixels in a picture, for example, and that would make a convolutional network really fail, but it could still work with other models. And so you have this this different kind of abilities that convolutional network just can't capture, like permutation here. And so better compare convolution with convolutional network in general.
And we had another quick question from the chat. It says here by Varun, how do you determine the weights? And this is in reference to the previous slide. And we had a comment by Shafak who said, the weights of the kernels are learned by the deep learning model through the optimization process.
Yes, that's right. So here we haven't talked about training, and we haven't talked about backpropagation. Actually, this chapter doesn't just focuses a little bit at the end of in the next section. We'll focus a little bit on training. But it's through the backpropagation mechanism that we studied in the previous chapter that we will learn these parameters. So there will be a few equations that show how to calculate the update equations, how to calculate the update to the parameters.
And there was another comment by Shafak in reference to Abdullah's prior question on how to determine the number of kernels. He says, each convolutional layer uses only one kernel. How many convolutional layers will be used in an architectural concern should be determined through experimentation, which is basically what you said previously, but I guess it's good to reiterate.
Yeah, there are some more theoretical choices that you can make, and how many, or at least if you're stacking multiple layers, how should you pick the number of kernels? Like in some networks, you'll see that the kernel size is increasing as you get deeper. For example, I believe AlexNet. I don't know if they will go through these. In this chapter, they don't go through these architectures. If you look at them, you will see that some of them use this increasing number of kernels as you get deeper before the fully connected. So there's some logic to doing that. Or some will use different kernels in parallel, different kernel sizes. For example, in the Google Net, I think we're using Inception module, which does multiple type of convolutional transformation at every level and sort of concatenate the output. And that works to some extent. So I think the strategy is that, yes, you can try things, but you also follow what other people have done in the past and take inspiration from that. And I think in the chapter on the practical methodology, they may go through more in detail about how to do those, to make those choices.
Thank you.
So the next section, 9.5, goes through variants of the basic convolution function. So like we said before, we were just considering a 2D image with one kernel. But in practice, the input can have multiple channels. So, and also we use multiple kernels in order to capture multiple features of that image. So I will go through so the mathematical formulation here, and try to make that clear through the pictures. So our input is V, is a picture with basically a picture has each pixel has 3 values, and so our input channel is the number of is basically those 3 different colors that you can capture. So it will be 3 for an input image. And then you have row J and column K. So that gives you a 3D tensor, Vijk. Sorry, not I, this is L. The channel number is L, LJK. That's our input V. And then the kernel will be a 4-dimensional one. So, and before I go into the kernel, now I'll say something about the output. The output is a 3D tensor. So we have 2 dimensions for the spatial, in 2-dimensional space, 2 spatial dimensions, row J and column K. So if you look at Z here on the right, Z, J, K, those are the 2 spatial indices. And then I here, I is the number of out channel. And really what it will be is it will reflect the number of kernels that one decides to use for this operation. So that will be the first dimension I here. So so we have multiple filters. Here I'm showing filter I. Each filter will be really 3-dimensional. It will have the spatial offsets for row M and for column N. So that's what we had earlier, right? For our kernel, we just had these 2 dimensions. But now we added this third dimension, which is the input channel size, which is the L here. So that will match the picture input channel. So if you're doing a picture, so this will be equal to 3, and our filter I will have the value will have 3 dimension along that axis, along the input channel axis. And so I show here in the picture 4 additional filters, and those will be the values along the axis I in K, Ki element. So we have 4 of these. And then for each one of these, the value will be reflected in the output channel value I. So if you look at the mathematical formulation, we're summing over values L, M, and N. So in the picture, we look at filter I. Those are the 3 dimensions of the filter. We're summing over these 3 dimensions. The input channel L, the offset M, and the offset N. And what we'll do is, similarly to before, we'll take these 3 dimensions, we'll overlay them to the input. We'll do these various products, V multiplied by K at these different locations, and then we'll sum everything. And that will be the value at location I, J, K in the output. And then we slide the kernel in these 3 dimension really, or sorry, in these 2 dimension, the offset M and N, then we do the same thing. And then also we do that for all the filters. So that will correspond to our output channel I index in the output. So it's Zi will correspond to kernel I. Yeah, so I hope that
there was a, yeah, that does make great sense. There was a quick question. So Dan Yang had asked, so is I the kernel channel and L the input channel?
Yeah.
But then, yep, then it seems he understood it. So he said, so I stands for the different number of filters. Is that correct?
Yes, exactly.
Yeah, okay, perfect.
So so when we talk about multiple kernels, that's the value of I, which kernel we're going to use. And once we fix that value, then we apply the convolution operation. So the output here, we have Z, I, J, K. So let's say we use the first filter, I equals to 1, and when we calculate Z1, JK, so for all values of JK, so there will be 1 plane in the output. And then we pick I equals 2, so that will be the second plane. And here in the output picture, I show 5 different planes, 1, 2, 3, 4, 5. And each of those corresponds to the 5 filters that I've drawn next to it. So these kind of 5 bundles of kernels.
Thank you. This is really in depth.
Okay, I'll just do it for this one. And kind of the thinking is similar to the other equations. So the next equation that we're given is the one that include strides.
Actually, we do have another really quick question. Sure. Varun has asked, what do you mean by channel technically?
So in the input, on the left side, V, the input channel will reflect the RGB, the 3 coloring schemes for a picture.
So red, green.
At every location that we have.
Yep. So red, green, and blue.
3 values. Yes.
Okay. Perfect.
That's in the input, and then in the output, the number of channel it reflects the number of filter that you're using at this layer. So once you perform the first convolutional operation, your input is a picture, and then your output is this Z variable here. Then if you go to the second level, if you if you do another convolutional area, and your input channel will be your out channel I here in the Z. So at that point, your number of channel is not your RGB colors anymore. It's just whatever you've applied from the different filters. And then it goes on like that.
Thank you.
Okay. All right, next one is the stride. And so in the previous version of the equation, we were just moving the kernel one position or one pixel at a time, but that can be computationally expensive. That can take more time, and we can decide to instead use different stride values. And so that's what stride means, is how many pixels should we skip in the spatial dimensions. So comparing the previous equation here on the top right to the new equation, with s being the value of the stride, so we see it's almost the same equation, except that we've added this multiply by s in the index. And so what it's doing, so here it's if s equals to 2, so we're basically gonna skip two pixels. And we're gonna move 2 pixels to the right. In that way. So that's kind of what this equation is capturing. Okay. So strides then can lead to downsampling if we're using stride. So it's actually so it can be good or it can be bad, depends on what you want to achieve. So if you are always using a stride of 2, like in this example, and if you do that to a number of convolutional network, eventually the shape of your input is going to shrink and become just 1. And so that might not be what you want. You might want to do other operation on the in the network. So zero padding is that sort of that concept that allows us to control the output shape of this operation. And it's really a hyperparameter, so you have to choose it. And there are 3 types. There's the valid padding, there's the same padding, and there's the full padding. And I added a link here that shows some of these animations, but I also created my own pictures. So the valid padding first is used in a way that your kernel should only fit the image shape. So it's kind of what we've been doing so far. The kernel here is contained within the image, like this red box, and then you move the red box to the right and then to the bottom. So you end up with a smaller output. So 3 by 3 if you're starting with 4 by 4. So the final width will be m minus k plus 1. So that's the formula. And if you're using same padding, then what you want to achieve is the same output shape as the input. So what you do is you add as many zeros as you need in order to maintain that shape. So in this case, we have a kernel of size 3. And so in order to maintain the shape, then we have to add 1 column and 1 row. I mean, we have to extend the picture by 1 pixel in each direction. And we set those to 0. And then we do the convolutional operation as before. We slide the window and calculate the values. And here, if you see the red rectangle, if we shift it to the right 3 times, we'll get at the end four values on the widths. And then if you go down 3 times, also we'll get 4 values. So we're keeping the same shape in the output. That's called same padding. And then full padding is when we want to go through, we want every we pad the input such that every pixel is visited k times, where k is the kernel size. So here I have k equals to 3. Then I have to add really 2 more columns, and 2 columns of zeros here before and above in order to do that. So as I slide the rectangle to the right, so every pixel will be visited 3 times. And so that will lead to a larger output of size m plus k plus 1. So wait, is this correct? M plus k, or is it m plus k minus 1?
While you're looking that up, we have another question from the discussion. Abdullah has said, from my knowledge at image processing, why Zorro padding instead of warping or ones padding? Are you familiar with the different kinds?
Can you repeat that?
Yep. Abdullah has asked, why do you use Zorro padding instead of warping or ones padding in image processing?
Or so zero padding is all these 3 types are called zero padding, and the 3 names are valid, same, or full. And so which one is he asking about?
He's naming a few others. One that's called Zorro padding, so that's Zoro.
Oh, I see. Okay, so I'm not familiar with
Zorro. And then
zero.
He also. I'm not sure if he misspelled it. Maybe it should be 0. There's like a minute delay between the video and the chat thread, so we'll see if he responds back. Okay. Yeah, so Shafaq says he thinks that he meant 0. And then also warping. Are you familiar with that process?
What is it?
Warping, warping.
Warping. No.
In reference to padding? Okay, well that's fine. Yeah, if you're not familiar with it, maybe someone else in the chat is familiar with it and they can answer that question. So you can continue.
Yeah, I'm not familiar. Is that, yeah, I'm not familiar with warping. Okay. All right, so so those are the three different types of padding, which allows us to control the output of the convolution net. So next is these 2 kinds of connections are discussed, the locally connected layer and the tiled convolution. And so they have a few different purposes. So the first one was used by LeCun apparently in his 1986 and 89 paper. And it uses the same connection graph, except that the parameters are not shared. So every connection uses a different parameter. And it's useful to use locally connected layer if you believe that each feature we're trying to learn is really just it's usually just a small part of a space, and it's not found in other part of the image. So we're not really interested in that equivariance property. And so that will be the formula, the algebraic formula for it. And our kernel here will be now a 6D to account for these new parameters. In the compromise between the locally connected and the standard convolution is the tiled convolution. And what we're doing here is we're using multiple kernels, and then we're repeating those to fit the input grid. So there is some more amount of sharing here. Immediate neighbors have kernels with different parameters. And so this also allows us to achieve lower memory requirement. And in the equation, this is captured with the modulo percentage here, percent symbol in the k index. So to show you how this looks like, we see here in this picture the fully connected network at the bottom. See, all nodes are connected together. In the standard convolution, we have sparse connectivity, like we said here, depending on the kernel size. And then we have this one kernel AB that's reproduced, that's used over all these other connections. So that's our second mid-level standard convolution. And in the locally connected network, we use the same graph connections, except that the weights, the parameters used are all different. So we have A, B, C, D, E, F, G, H, I. Well, in the standard convolution, we had one kernel of size 2 with AB, and then we repeat that. And then in the tilted version, in the tiled version here, in the middle figure, we're basically reusing a number of kernels. You can see it like that. So here we have two kernels, A, B, and C, D, and then we tile them. So we use the first one, then the second one, then we reuse the first one and the second one. So in red is the first kernel. So that's the difference between the two. And yeah, again, this allows us to so depends on our task. If in our task we don't have this requirement that we want equivariance for translation, that our features are really locally located, we may just use locally connected. And then otherwise, if we want a compromise between the two, it's even said that we might be able to learn a set of weights that we can rotate through the space, frankly. And then we can use the tiled convolution for that purpose. But yeah, there's a little bit more detailed in the book that goes through that.
Thank you.
Yeah. Okay, the last section, I think going on to the hour. We'll go through, so there's a small section on training. He doesn't really go into deep details, but he provides the following information. So first is that we recognize the convolution itself as a linear operation. So it's this sum of products. And we can think of it as this one big matrix that we're creating and multiplying with the input. And the content of this matrix will be sparse, a lot of zeros. And also each element of the kernel will be copied in multiple locations, so to kind of fit that double summation. So one can think of it like that, this as a matrix. And then once we form this matrix, we're actually going to use the transpose of it when we're doing backpropagation. And this matrix is also, I think, used for what is called deconvolution in the literature, but better called transpose convolution. And it's used for reconstruction of inputs and visualization of the networks. And he doesn't really go into that in this chapter, but there might be another chapter that goes into that. Maybe. Okay, and then we go through a simple example of deriving the equation. So let's assume this trident convolution with this kernel K, multi-channel input V, and stride S. So that's that equation we've seen before. And we have a loss function, J. And so we went through backpropagation in the previous chapter. So when you do backpropagation, at the output of this module, of this convolution module, you will get the derivative of the loss with regard to the output. That's kind of coming in. And then you will use that to calculate the derivatives with respect to your weights, and then as well to the inputs if you have further levels going down. So so he calls J or sorry, G, that tensor. And it's the derivative of the loss J over the output C. So the next is to do the derivative with respect to weights, to the kernel weights. So we're looking for the derivative of the loss, delta J, over the kernel parameters. And so this is the formula. And you can think of it, I mean, it makes sense when you think of the derivative to be equal to the derivative over G and then the derivative of G over K. And sorry, the derivative of J over, sorry, the derivative of J over Z, the output, and then the derivative of the output over the parameters. So you see inside the summation here appear the J, and then as we are deriving over the K's, and it's a linear function, so what remains are the V's, the input values, and you have to get the right indices in place for the summation. So that's the derivative with respect to weights, and the derivative with respect to input V will take a similar path, and then will lead to this tree summation. Now he has more details in this report. In the I put the derivation details at this location, so so you can go there, and it will go into the steps, to every step of this derivation. And then one final thing is that typically the output of the convolution goes into a nonlinearity, like a ReLU. And so, and we expect a bias as well. So how to apply the bias? So three different cases. If you're using a locally connected layer, then you can associate a bias with every unit. If you are using a tiled connection, sorry, tiled convolution, then you can share biases with this same tiling pattern. So so the whole tiling will have one bias. Or if you're using standard convolution, then you can use one bias for each channel. So these are the three ways to do it. So I will end here, and then next week I can go through the remaining of the section.
Wonderful. Thank you so much, Sharif. That was super in-depth, and the slides were really, really great. So thank you for taking the time to put those together for us. We're looking forward to part 2 of Chapter 9 on convolutional neural networks next week. So that'll be the same time on Saturday here at 11 Pacific Standard Time. And then also, so just to reiterate for anyone that joined us after the fact, so what we're doing is we're reviewing the deep learning book online, basically going chapter by chapter, actually half a chapter each week at this point. And we do have all of our presenters or volunteers. So they sign up online on the presenter sign up form, which you can find either in the meetup group per event, or also right underneath the YouTube channel. If you get an opportunity and you want to take the time to read the material ahead of time, put together a little presentation for us, we really appreciate all of our volunteers that do that. And then also, if you'd like to join us in person, if you happen to be in the San Francisco Bay Area, we also meet on Mondays to cover the same book in person. Those discussions get a little bit more lively because everyone's in one room at one time, so it's a lot of fun. And so people can like draw up pictures and really explain what's happening, which is great. And that happens at Sandbox Suites in San Francisco. So that's another option. We also had a Thursday night meeting as well, but we temporarily discontinued that one. So we'll be starting that one up again soon. Keep an eye out for that. We also have some awesome workshops and events coming up soon. So our next workshop, actually our next global workshop, is going to take place in Oslo, June 12th and 13th. That's Oslo, Norway. So we had one previous one there, so this is going to be our second one there, which is super exciting. We also have in the Bay Area a really cool hackathon that we've been working on. So this is the AI and Genomics Hackathon, and that for this hackathon specifically, we're really lucky. We have a patient that has been diagnosed with a very rare type of cancer called NF2 tumor cancer. And so he is actually donating the data set of his genome sequence for us to use during this hackathon. So the goal for this is to basically try to find alternative treatment options, or really to try to discover as much information as possible and kind of further the research in this area. So artificial intelligence and genomics is a very new, exciting area to kind of dive into, and there's tons of different medical applications that can be found from doing this type of research. So I hope people can join us for this. It is a free event, a free hackathon. We're partnering with some really cool groups for this hackathon, so including Google Launchpad is where it'll be taking place in San Francisco. We're also partnering with one of the Stanford labs and the Berkeley lab for that as well. We'll have speakers, a panel discussion, obviously the presentation, some prizes, which I'm not going to tell you what those prizes are yet, but you'll just have to join us to find out. I'll be posting that event as well on the Meetup group, but it's also available if you follow us on Facebook. You'll see the event page. It's also on Eventbrite. And we're also partnering with the San Francisco Silicon Valley Artificial Intelligence nonprofit group for that one as well. And all this information is also available on our website if you go to www.accel, that's ACCEL.ai. And then our next workshop in the Bay Area is going to be happening in July. And that workshop, we're partnering with some different groups. We're partnering with another engineering boot camp, which focuses on educating women and people of color within specifically the East Bay area. We're also partnering with the Women Who Code East Bay chapter and Pi Ladies of San Francisco, so specifically a group that helps women learn Python. So a lot of amazing partnerships, a lot of amazing groups that we're partnering with to kind of bring you these events and workshops, and we have presenters that volunteer for all of those. So thanks to everyone who makes that possible. So yes, definitely if you want to join our group and kind of follow along and get involved in the community. We also have a Slack channel, which unfortunately isn't as active as I would like, but we have a Facebook page, Facebook group, and we're trying to really branch out and create these different events for people to get to know and learn artificial intelligence. So thank you again, Sharif, for presenting for us this week. We really appreciate your time and effort. We'll definitely be seeing you next Saturday.
Thank you.
Do you want to say anything else before we sign off?
We have a lot of exciting things definitely for everybody to check. So thank you for this, and if anybody has more questions or would like to follow up on any of the question asked, you can reach out to me. I have the email on the presenter form, and I'm looking forward for next week presentation, second part of the convolutional network chapter. Thank you, Laura, again. Thank you, everyone.
Yes, thank you. Thanks, everyone. Okay, so we'll be signing off on this amazing Saturday. Go outside, enjoy the sun if you're in San Francisco. Yeah, and we'll be seeing you soon.
Bye-bye.
Bye, everyone.